Okay, so in our getting used to the notation of differential equations and playing around with what it means to be a solution, this is one of the things we can do just to get us started. So I have a differential equation that I'm starting with, dy dt is equal to k times y minus a, and I have a proposed solution, y equals a plus c e to the kt. And we're just supposed to decide whether or not that actually does satisfy the differential equation. So one thing I want to point out is as soon as I write down dy dt, that tells me that I should be thinking of every y as representing my mystery function and as every t as my independent variable. So I should be thinking about the k and the a as constants in this problem. So if I want to know if this satisfies the equation, how do we verify solutions? We just plug them back in and check. So I can replace the y with an a plus c e to the kt, but I'll also have to replace the dy dt with the dy dt of my proposed solution. So the derivative of my proposed solution, a goes away, c e to the kt is going to be itself, but then you'll chain out the derivative of kt, which is k. So plugging back in over here, is it true that ck e to the kt is equal to k times, replace y with a plus c e to the kt minus a. So first thing I notice is that the a's cross out, and I'm left with ck e to the kt equals k times c e to the kt, which looks fantastic. So I'm going to say yes, in fact, I do think that is a solution. Okay, so kind of continuing in that same sort of thinking, we can get a little more specific and say, okay, well, what if I propose a solution, but it's only true sometimes? Can you help me figure out when it actually works? So in this one, we want to find the values of constant k that make it true that y equals cosine kt plus 1 satisfies our differential equation d squared y dx squared is equal to negative 5y. So that differential equation says the second derivative of my function is negative 5 times my function. So the process here is going to be similar to the last one. We're proposing that y equals cosine kt plus 1 is a solution. To check that, we'll actually need to figure out what its second derivative is. So dy dt is equal to, derivative of cosine is minus sine kt plus 1, and then we have to chain out the derivative of kt plus 1. Notice again, oh, this is a mistake, this should be a t, sorry guys. T is our variable, so k is just a constant. The derivative of kt is going to be k, and the derivative of 1 is 0. So when we take our second derivative of function y with respect to t, we're going to get derivative of cosine, our derivative of sine is cosine, the minus k just hangs out, kt plus 1, kt plus, I'm really going to lose it with this pen. And then we have a chain rule again. We chain out another k, so this actually becomes k squared cosine t. So we were supposed to figure out how to make it true that this thing, the second derivative of our function, is equal to negative 5 times our function cosine kt plus 1. So again, I'm just referring to this differential equation, and it says the second derivative of your function is equal to negative 5 times your function. So right off the bat, I can see that the cosine kt plus 1 matches regardless of the value of k. It doesn't matter what k is, those are fine. I can also see, whoa, excuse my slidey screen, that the minus signs aren't going to be an issue. What I really care about is that the k squared has to equal 5. So this will be true if k is equal to plus or minus the square root of 5. And let me peep back and see. I don't see any reason why I would care about negative, not giving me any trouble or anything. So I'm going to say those are both perfectly good answers. Okay, thanks for watching.